Hello everyone, welcome to this workshop. My name is Hong Xu. I'm a product engineer on RAS team. Joining me is my colleague, Semester Chatterjee. She is a product engineer on spatial analysis team. In this presentation, we'll talk about how you can leverage ArcGIS platform to work with your multidimensional scientific data. By scientific data, we mean ocean data such as temperature, salinity, weather data like precipitation, wind speed, climate data, atmospheric data, and so on. The data may come from satellites or collected from observation stations or calculated from model simulations. Most of the data are graded data, raster data, but some might be points or tables. Regardless what form they are, these data all represent measurements at certain times or depths. So we call these data multidimensional data. ArcGIS is a platform for your multidimensional data. First, ArcGIS supports many data types. With ArcGIS Pro and ArcGIS Enterprise, you can visualize, manage, and share your data. Second, with extension products, you can perform raster-based and feature-based analysis and create many analytical maps. And third, ArcGIS Online provides rich contents for science, ranging from weather, ocean, climate, and water, and so on. So that was an overall platform story. In this presentation, we'll first go over the user experience for working with multidimensional data, and then we'll set our focus on RAS data, introduce multidimensional RAS API for Python programming, discuss and demonstrate how to manage and analyze your multidimensional raster. We'll talk about sharing multidimensional raster, and at the end, we'll have time for questions. ArcGIS supports many multidimensional formats. netCDF is the most popular format in the science community. There are a few specifications out there. ArcGIS follows CF convention, climate forecast convention. If you want your netCDF to work with ArcGIS, create by following the CF convention. HDF format is often used by NASA to distribute scientific products. And ArcGIS favors HDF US style metadata. So follow this convention if you want your data to work with ArcGIS. GRIB is WMO standard for storing weather data, and OpenDAP is a web protocol used by many organizations to share data. ArcGIS can read all these formats directly as multidimensional raster. ArcGIS also has its own multidimensional raster formats. Multidimensional mosaic dataset is used to manage multiple files and brings multiple files as one multidimensional raster. Multidimensional CRF, cloud raster format, is designed for multidimensional analysis. We'll discuss more in the data management section. Multidimensional image service obviously is the service published from a multidimensional raster. While most multidimensional data are raster, netCDF can also store feature data, such as data collected from stations. For netCDF feature data, you can make netCDF feature layer tool to add as a feature layer into Pro. With feature layer, you can leverage all tools that works with feature data. Query, animate using time and range sliders, perform analyses such as space-time cube, hotspot analysis, and so on. So we'll have one demo on feature data. And other than that, all the rest presentations will be on multidimensional raster. So what exactly is a multidimensional raster? A multidimensional raster contains one or multiple variables. For example, you can have temperature, salinity, ocean current variables in one file, and each variable can have spatial dimension, time, or depth. You can consider a multidimensional raster as a cube, where each slice is a 2D array. It's a raster. ArcGIS Pro provides an integrated user experience for working with multidimensional raster. From Layers Multidimensional tab, you can access tools to visualize, explore, analyze, and manage multidimensional raster. You can select variables easily, step through slices and animate slices easily, and you can visualize temporal profile at any given point or at an area of interest. For wind or ocean data, you can use vector field render. And you can also display your netCDF data as a 3D volume using voxel layer. The Make netCDF raster layer tool becomes legacy tool. We'll continue to maintain it, but if you want to take advantages of the new capabilities, we suggest the Make multidimensional raster layer tool. You can create a multidimensional raster from all formats with this tool: netCDF, GRIB, HDF, or OpenDepth. So what you can do from the web. The web map viewer for image service has a multidimensional filter. You can filter by variables, by slices. You can access the pre-configured templates to process the images on the fly, or use the multidimensional analysis tools and functions to perform analysis. You can use the time slider and dimension slider to animate and work with image service, multidimensional image services. So that was a quick overview. Now I'm passing to Samantha, who will demo data exploration in Pro.
Thank you, Hong. Hi, I'm Dr. Shormishta Chatterjee. I'm a product engineer in the spatial analyst team from Esri Redlands. Let me start by giving you a quick overview of all multidimensional functionalities in ArcGIS Pro. From the multidimensional toolbox, you can now read, write, and manage multidimensional data as a raster, feature, or a table. Analytical tools are available from the Image Analyst and Spatial Analyst toolbox in the Multidimensional Analysis toolset. Now let's add some multidimensional data. Multidimensional data can be observed or modeled at stations, trajectories, or as continuous surfaces. For example, I have downloaded an INCOM model output from NOAA as a netCDF file, and I am interested to look at the water temperature variable. So I'm going to use the Add Data dialog to ingest the INCOM netCDF data. I'm going to select the variable water temperature and add my data. It's that simple. Now in ArcGIS Pro, you have a multidimensional ribbon to work with multidimensional layers. For example, you can visualize the water temperature multidimensional raster slice by slice, or you can animate through time or depth. You can also explore how the water temperature changes using the temporal profile. From the multidimensional extent, you can specify a variable, a start and an end time, before doing any analysis. All multidimensional data management and analytical tools can also be accessed from this ribbon. These tools are same as available from the toolbox. Now let's look at another example. I have downloaded a day-made daily rainfall station data in centimeters from Oak Ridge National Lab, and I am interested to look at the observed rainfall data. This data is non-gridded or irregularly spaced, so I'm going to use the Make netCDF feature layer tool to read the data. I'm going to specify my netCDF file. I'm interested in the observed rainfall variable. I'll specify the X variable and the Y variable, and I'll specify stations as my row dimensions. Since I'm not specifying a dimension value, all the data from all the slices will be added. By default, I can see the observed rainfall from the first day of the year, since this is an annual data. If I'm interested to look at a different day, I can use the Select by Dimension tool on this Observe Layer output. For example, in this case, I am looking at 1st of July. I can also create just a table with the rainfall values if I'm not interested to see the stations using the netCDF table view tool. Now, back to you, Han.
Thank you, Semester. Next, we're going to look from Python developer's view, discuss the Python environment for working with multidimensional raster. Python is a great language to do data science, and ArcGIS provides a platform for you to work with multidimensional raster using the programming language you are familiar with. ArcPy is a desktop application where you work with local files, services, but the process is done locally, and the result is saved on your local machine. You will import arcpy.ia, which is the image analysis module for ArcPy. And ArcGIS API for Python is an enterprise application. You use it to work with your image services, web layers. The processing happens on server side, distributed across all servers available in your portal. And the output is created on server as a hosted image service. For API for Python, you will import ArcGIS.raster module, raster functions, raster analytics modules. For multidimensional raster, the programming patterns between the two products are very similar. So in this presentation, we'll use ArcPy in slides and in demos. The main API to work with multidimensional raster is the raster object. Same object as you work with a regular raster. But for multidimensional raster, you instantiate the object from a multidimensional raster file, an SDF file, a CRF, or from a multidimensional mosaic dataset. The raster object works with raster functions to perform on-the-fly multidimensional analysis. You can call these functions directly from ArcPy or from API for Python. Raster objects works with multidimensional analysis tools to generate analytical results. Of course, you can create custom raster functions or custom geoprocessing tools to extend the capabilities. In the diagram, there is a raster collection class in gray. This workflow is mainly designed for working with time series imagery, and it will be discussed in an advanced session which is listed at the bottom. So now let's look at how you can use these APIs to do data management. We'll cover access, create, and process multidimensional raster. Creating a raster object from multidimensional raster data is very straightforward. Simply call arcpy.raster, set the data path, and set its multidimensional parameter to be true. You can create directly from a file such as netCDF file or a mosaic dataset. If you want to access a multidimensional raster in a cloud storage, simply including the connection file in the path. In this example, the file with .acs extension is a connection file to a S3 device. It opens a CRF in that S3 device. To save a multidimensional raster, use raster.save. You can save to a CRF with current release. Next release will support save to netCDF. However, in many cases, the data you work with are multiple files, and you want to aggregate all as one multidimensional raster. In this case, the mosaic dataset will come into place. Mosaic dataset is a data model that manages multiple rasters. In the context of multidimensional raster, it manages variable names, dimension arrays, and other metadata as geodatabase table, where each row is corresponding to one raster, a 2D array. Mosaic dataset does not store pixel data, but reference them and process the pixels on the fly. Because mosaic dataset is based on geodatabase tables, so it is very flexible in terms of adding data, appending data, inserting, and deleting records. So now how do you create a multidimensional mosaic dataset? It basically involves two steps. First, you create an empty mosaic dataset, which is the container, and then add data using add rasters to mosaic dataset tool with a suitable raster type. For example, if your data is landsat, use landsat raster type. That's all. All the data within the input folder will be added to the mosaic dataset. You can select a few variables to add or choose to add all variables. If you want to create a mosaic dataset from Landsat images or TIFF images, you can use Landsat raster type to add, or use raster dataset type for TIFF images, and then use build multidimensional info tool to build multidimensional info. For your reference, here is a link to a blog that shows the 3 workflows. CRF is an Esri's multidimensional raster format. It is optimized for cloud computing and multidimensional raster analysis. CRF stores variables, dimensions, and pixel data. Data are stored as tiles and can handle parallel write, parallel processing, and distributed computing. A multidimensional CRF can store a transpose, which is a flipped cube designed for dimension-wise access. For example, extract pixel time series data to draw a temporal profile. It is very efficient for long time series data. CRF supports log compression, a very efficient compression algorithm for scientific data. To create a multidimensional CRF, simply call copy raster tool. It will copy all variables to a CRF. If you want to have certain variables, use make multidimensional raster layer and then copy. The code snippet creates a layer from an OpenDepth URL and save as a multidimensional CRF. You can update the CRF with new data. We'll get to that in the next slide. Besides creating multidimensional raster, you might want to do other operations. Subset is a very useful operation. You can subset by time, by depth, with a list of values, or with a range. Very flexible to create a subset of the data. I would like to mention here, we have subset function and subset multidimensional raster tool. Subset function does not write output on disk right away. It defers the operation until you call save. The GP tool always creates an output. We provide a function beside the GP tool because it is very useful to have a function like this for certain operation. So you don't have to spend time on creating output when not necessary. This also applies to merge. Merge two multidimensional raster into one. So we have a function and also a GP tool. I mentioned in the previous slide that you can update CRF. Manage multidimensional raster is the tool to do that. You can append slices, update slices, you can add a variable and remove a variable. So this is a very useful tool to update your CRF with new data and maintain a live CRF or live image service. Now let's switch to Semesta, who will show some more demos.
Thanks, Hong. Now let's look at the income netCDF data that I downloaded before in Python. To read the data, I'll import ArcPy and the image analysis module and create a multidimensional raster object from the netCDF file by setting multidimensional equals true. Now that I've created an object, I can explore the data by looking at the variable. I can see all the variables that are available in this dataset. To explore further, I can get the empty info property. This will give the details for every variable and dimensions. Now let's take a look at the water temperature variable again. for one given time. If I look at the MD info, I can see that this output still has all depths, but the data is now a subset for one time only. I can further see the slice with one time and only the first depth. Instead of doing this in two steps, you can also do it in one go if you know which slice you want to explore. Now we know how to ingest data from a single multidimensional file, but oftentimes we work with hundreds of different files for different regions, or time steps, or depth. So I can manage these files using a mosaic dataset to create a continuous, seamless layer. For example, I want to analyze the global snow coverage data for the last 20 years, so I downloaded the MODIS snow cover monthly data from NASA, which were available as HDF files. I'm going to manage this data by creating a mosaic. Now, creating a mosaic is a two-step process. I'll first create an empty mosaic dataset and then add rasters to it. I'm specifying HDF as my raster type, and I'm specifying my input path. Since I'm not specifying a variable, the mosaic will be created with all the available variables from the HDF files. Now from the MODIS user guide, I know that I'm interested in the values only for 0 to 100 for snow cover percentage. So I'm going to use the mask raster function to only get the values between 0 and 100. Finally, I'm going to save my output to a cloud raster format for further analysis using the copy raster tool. These tools allow me to build a multidimensional transpose, which will enhance the performance when accessing pixel values across all slices in a large multidimensional dataset in just one step. Now, if I run this script, this is how my output will look. Most of the snow coverage is in the northern hemisphere above 45 degrees and in the high mountains below 45 degrees. That's how we can read and manage scientific graded data. Back to you, Hong.
Thank you, Semester. Now it comes to the analysis section. We'll cover analyze using multidimensional tools, RAS functions, map algebra, and customization. Starting from Pro 2.5, we have developed many multidimensional analysis capabilities. Aggregate allows you to aggregate your data based on your defined temporal resolution or dimension resolution. For example, you aggregate your daily temperature into monthly to look at monthly average. We provide many handy keywords like yearly, monthly, quarterly, daily, and so on. You can also define your own interval to aggregate. Anomaly allows you to look at how different of your data from historical mean or median or z-score. The tool will calculate the statistics from the input data. You can also use an external raster as the base to calculate the anomaly. With the Generate Trend Raster tool, you can perform trend analysis, for example, to look at sea surface temperature trend in the last 30 years, and then use the Predict tool to generate future data. We support linear model for annual data and harmonic model for seasonal data. In Pro 2.7, we have added main candle and seasonal candle methods. These are for trend test, non-parametric model, not for prediction. Find argument statistics tool allows you to find at which date the data has reached its highest or lowest value. Another category of multidimensional analysis is change detection. We support two algorithms, CCDC and LandTrender. You can check out the demo theater for detailed discussion on change detection, There's also another demo theory on prediction and trend analysis. You will see more in-depth discussion on that topic. Sometimes you want to extract and enrich information from your multidimensional raster. For example, you study certain species or endangered animals, and you have observation data with locations and the times these animals appeared. You can use sample tool to extract the environmental variables at these locations and time, and study the animal habitats. Sample tool has been enhanced to support points data, polygon data, and other geometries. You can also set the time or time range for your location. Statistic tool has also been enhanced to support multidimensional raster. The output can be a raster or a table with statistics per zoom. You can perform multidimensional raster analysis using RAS function. A RAS function is an algorithm definition for processing RAS data, and it supports on-the-fly processing. You can chain the functions to solve a complex problem. You can also save the RAS function as a processing template, RFT. A RAS function can support multidimensional analysis if it is made dimension-aware. When such a function is applied on a multidimensional raster, it will process each slice, all slices. All local RAS functions and many other functions are made dimension-aware. For example, if you have a temperature data of 30 years in Celsius and you want to convert to Fahrenheit, just simply call a RAS function unit conversion function. It will apply to all slices. If a function involves multiple inputs, it can also perform slice-by-slice operation, but make sure to set this environment settings to be false, because by default it works with variables of same name. Multidimensional raster also supports map algebra operators. Map algebra has been a very useful feature in RAS analysis. Now you can apply it to multidimensional raster. It makes the calculation and the programming much easier and simpler. If the built-in tools and functions do not meet your need, you can create your own ones. NumPy is a package for ND-array handling. You can use raster.read or raster.write to interact with NumPy array. For large dataset, you can use pixel block collection to iterate the pixel blocks. You can also use ras to NumPy ras function to interop. This function is lower left corner based, while raster read is upper left corner based. So something to be aware of when you choose which one to use. Xarray is a new package emerged in recent years for ND array handling. It is better because the arrays are labeled, very much like our multidimensional raster information model. Very easy to use. So you can get Xarray from raster using ras to Xarray function, and then you use Xarray functions to process the data. For example, resample along a dimension, and then convert to raster using Xarray to raster. Another way is to develop a Python RAS function. You can deploy a custom Python RAS function in Pro and in Enterprise. It will behave like the built-in RAS function. I recommend you attend the Advanced Custom RAS Function using Python session if you want to learn more. So again, let me pass to Semester for some interesting analysis demo.
We often annotate point location with environmental variables from multidimensional raster. In this example, I am going to annotate point location of the endangered North Atlantic right whales with sea surface temperature at animal home ranges for August 2015. This process is called environmental annotation. I'll use the whale observation data collected from the Ocean Biodiversity Information System and the sea surface temperature multidimensional data from the ArcGIS Living Atlas. Before I start to annotate, let's take a quick look at the data from the data clock. From the data clock, we know that most of this data is available between the months of July and September for the year 2008 to 2017. I'm going to specify August 2015 as the time slice and a home range to annotate the whales. First, I'll specify the necessary modules, environment and data folders. Next, I'm going to prepare the multidimensional data. I'll read my sea surface temperature data from the Living Atlas using the Make Multidimension Raster Layer tool. Finally, I'm going to use the sample geoprocessing tool to create the spatial and temporal aggregation around an observation before doing the extraction. I'll specify standard time and event date as the acquisition definition and 10 as my buffer distance. In the table output, observations only from August 2015 were annotated considering the spatial buffer for the analyzed sea surface temperature. And from the standard time column, you can also see the exact dates when these whales were observed. This way, you can annotate a series of points with multidimensional data. Now let's look at another example. I want to compare the growing degree days or GDD between 1980 and 1990. GDD is an indicator of heat accumulation and is used to predict plant and animal development. To accomplish this, I'll combine data from different datasets, perform map algebra, and do an aggregation to get the monthly growing degree days. I'll start by importing the necessary modules and packages. I'll define the input and output data path and set the environment. I have daily maximum and daily minimum day-met surface temperature data for 1980 and 1990 in 4 separate netCDF files. In order to do the calculation, I'll combine the maximum temperature of 1980 and 1990 in a single multidimensional raster object. From the multidimensional info on the raster object, I can know more about the multidimensional property. I'll do the same for the daily minimum temperature. Now I have 2 multidimensional raster objects, one representing minimum and the other representing maximum temperature. I need to do a slice-by-slice operation between these 2 multidimensional raster containing 2 different variables. To ignore the variable name for further calculation, I'll set the match multidimensional variable environment to false. Here I'm going to calculate the difference between the average temperature and the base temperature. This is a simple map algebraic expression but will be applied to the entire cube. Now using the base temperature as 10 degrees, I'll calculate the number of growing degree days. I'll remap it to represent only the positive values. I'll look at the GDT for June 1st and use a color map, slope color map renderer to visualize the difference. The next step is to calculate the monthly GDT. To calculate the monthly growing degree days, I'll use the aggregate raster function to sum the values using month as the interval. Now I'm expecting 24 slices for 24 months instead of 730 slices for 730 days from the 2 years. Here again, I can visualize any given slice. And finally, save and persist the dataset. Next, let's look into the global trends and anomalies of how snow cover is changing over the last 20 years. For this analysis, I'm going to use the snow cover CRF dataset that I created from the MODIS data in an earlier example. For this example again, I'm first importing my necessary modules and packages. I'm defining my input and output data path, and I'm setting the environment. Now let's explore the snow cover dataset. The data has two variables and has monthly snow cover percentage data from 2000 to 2019. To know more, I can explore the multidimensional information property for this raster object. Instead of looking at the snow cover on a monthly basis, I want to look at the yearly mean. So I'm going to aggregate my data using the aggregate raster function to calculate the mean and specify my interval as yearly. While this is helpful, I want to look at the snow coverage that is significantly different from the mean. So I'll use the aggregated data to calculate the difference from the mean using the anomaly raster function. And I'll select difference from mean. I can choose a renderer to make a more meaningful display. And finally, I can save my output. Now let's take a closer look at the outputs we just created. This is our monthly snow cover data. This is the aggregated yearly mean for the last 20 years. And this is how the anomaly output looks. The output shows areas with higher and lower values than mean snow coverage. I can change the time window on the time slider to look at the different time slices, or I can animate through the entire time period to see how the anomaly changes. That's how you can analyze feature and raster data, extend the analytical capabilities using existing tools, properties, methods, classes, and functions. You can build your own script tools using ArcPy, SciPy, and many other Python packages. We hope that these new tools and capabilities will help you in your workflows. With that, back to you, Han.
Thank you, Samantha. We have discussed managing and analyzing multidimensional raster. You can also share your multidimensional raster through ArcGIS Enterprise. You can share your multidimensional raster as an image service or a map service. Image service serves data and support on-the-fly processing. You can also perform raster analytics using multidimensional raster analysis service tools. A multidimensional image service also supports WCS and WMS with dimension query. So in general, we recommend using image service. There is one case you might want to use map service is that you want to include both raster and feature layers as one map and publish as one service for mapping and visualization purpose. You can publish image service using Pro or from the web using Create Image Layer Wizard. From Pro, you can publish from a mosaic dataset or a CRF. In web, besides these two data types, you can publish from a file such as netCDF directly. It will convert internally to a CRF and create a hosted image layer. To support on-the-fly processing, you can pre-configure processing templates. For example, your data has temperature and humidity variables. You also want to serve heat index data. Instead of creating heat index data, you can define a heat index template and add it to your dataset. When published, you can access the processing template from the web viewer and display the heat index data on the fly. Mosaic dataset and the CRF can all store processing templates, where the CRF support is added in 2.7, Pro 2.7. So let's take a look at a demo on sharing and consuming image service.
Now that I've explored some datasets and created new information from my analysis, I would like to share some of the multidimensional data with my colleagues within the organization and outside the organization for further analysis. I would like to publish the snow cover yearly mean aggregated data that I created from my last example. To publish, I would right-click on the data from the catalog and share it as a web layer. Now to publish a data, I must have administrator or publisher access. I'll give it a name, a summary, and some tags. I'll share it with everyone to make sure internal and external users can access it. From the configuration pane, I'll enable WMS and WCS so that other clients that require OGC standard can consume it. And then I'll publish my data. You can also automate the publishing process by using scripts. For more resource, see this reference page. The data I published shows up as a portal item now. I can open it in a map viewer and do further analysis on it. From the map, we see that this data retained its multidimensional capability. Now let me zoom into a smaller area. Now I want to see the snow cover trend over the 20 years. So I'm going to use the multidimensional analysis map viewer tool, generate train raster. I'm going to specify my aggregated data, the snow cover as the variable, and I'm going to select a linear trend. Since we selected a linear trend, each pixel represents a linear slope for the trend line. The reddish area represents where a significant trend has been observed in the last 20 years. We can use any geoprocessing tools and raster functions that can take an image service as input and do further analysis on it. That's how we share and consume multidimensional data for analysis. Thank you. That's all from me. Back to you, Hong.
Thank you, Samantha. We have finished our planned slides and demos. I'd like to point you to some additional resources. The ArcPy and ArcGIS API for Python references. There you can find usage tips and samples. There are also tutorials on image workflows, many learn lessons and blogs on multidimensional rasa analysis. These are very good resources to learn. And always, please provide your feedback for this session by clicking the session survey link directly below the video. And with that, I'd like to end the presentation and we are ready for questions.
Hi, this is Norman with my colleague Hong and Sharmishta. They are the presenter. Thank you for attending the session and submitting such a great question. So I'm going to turn around and ask this question to one of the presenter and they will answer your question. So the first question I have, I want to publish image service from some weather data in netCDF format. Should I create a mosaic dataset or convert them to CRF? Hong, you want to take it?
Thank you, Norman. And this actually is a very good question, and there is not like a single answer. And so it really depends on the type of application, the type of service you want to create, like what the purpose, the role of the service, or like the size of your data, or like where is your service is going to be located, like is it in cloud or on premise. So, but in general, the CRF format performs better than mosaic dataset by the trade-off of some actual space, because you want to create the CRF and store all those pixels, right? But if you're willing to just spend some actual space, disk space, because disk is cheap, right? But then creating service using CRF is actually better. Because, for example, if you want to publish a service and want to support things like temporal profile operation, like create a time series at given location. And then the best practice is to create a CRF and build a transpose, because CRF support transpose, which perform better for a dimension-wise operation, right? And then if you want to create a service, image service out of multi-dimensional data in the cloud, and regardless what type of application, CRF is the best choice, because these netCDF or GRIB or those multidimensional formats, they don't perform as well as they do in cloud as they do in file system. So CRF is the solution for that type of applications. However, if you say I don't want to spend actual time or disk space to store the CRF, I just want to publish my service and to support like this display and slice by slice type of application, then mosaic dataset is still a good solution for you.
Thank you, Hong. Our next question is, I notice all the analysis result in the demo are saved as CRF. Can you save to netCDF format? Sharmishta, you want to take it?
Sure. Thanks, Norman. Yeah, you can absolutely do that. For all our analytical tools, analytical multidimensional tools, you have the option to save it as a CRF or to save it as a netCDF file. You can only change the extension, so in the output format. So if you specify .nc instead of the default, which is CRF, if you specify .nc, then your output will be a netCDF file.
Thank you, Sharmishta.
Oh, sorry, I want to add some addition this. Yeah, so it depends on which version of the software you are using. If you're using 2.6 or 2.7, yes, so CRF is the only format. But then, very soon you will be able to save to netCDF, which is .nc, and then it's in Pro 2.8.
While you are actually are in the format question, there is another question came in, Hong, see if you want to answer it also. Did I see the netCDF can go straight to CRF and skip building a mosaic dataset?
Then CRF.
So can somebody can create a CRF from netCDF directly without creating a mosaic dataset?
Oh, that's yeah. Yes, you can. Right, because if you work with one netCDF file, right, you can create a layer and save the layer as a CRF. And then if you work with multiple files, and the workflow will be you create a mosaic and then you save the file as a CRF.
Thank you, Hong. The next question is, when working with the OpenDAP data, which tool should I use? Make OpenDAP raster layer or make multidimensional raster? What is the difference between these two tools? Hong?
You ask me. Okay. Yeah, so kind of touch a little bit on this topic using the make netCDF layer tool. And this make OpenDAP raster layer tool is a similar situation. This tool is built using a previous technology. It supports slice by slice operation. And if you just want to visualize the data, you can use this tool. However, the layer created by this tool doesn't support all the multidimensional analysis tools functionality. So if you want to take advantages of the new capabilities, we recommend you use the make multidimensional raster tool.
Okay, thanks, Hong. So let's go to Sharmishta with a quick question. I'm sure that many users are wondering about. Will you be sharing the Pro project and or notebook from the demo? Sharmishta?
Sure. Yeah, all of this, the presentation that we did, it will be available as a recorded presentation, so you'll be able to see it later on. It will be
But
available.
will you be able to share the notebook or the project itself?
Right now, we are not planning to, but if you are really interested, you can email me. So my email is schatterjee, CHATTERJEE @esri.com. So if you email me, I can send you the project and the notebook.
Okay, thank you. Um, next question is for Hong. What tool would you use to find the average over time for each pixel? For example, compression the box into one raster to use it in a suitability analysis. So it's a dimensional reduction question. Hong?
Okay. We have this multidimensional aggregate multidimensional raster. This tool is designed to work with multidimensional data. So you can average for each pixel. You can average over all slices, or you can average by given interval, like yearly, monthly. That will provide many keywords. So in general, you can just use aggregate multidimensional raster tool with the default operation, which is all slices, and then just it will compress into one slice, which is what you need.
Okay, thanks, Hong. There's another question for you. Are the methods for changing the projection of data transform from one specific projection to another? So can we do this thing job in ArcGIS?
Okay,
Changing
so
projection of the data.
right, I think this probably be specific to multidimensional raster. I think, say, if for a regular raster, non-multidimensional raster, we have project raster GP tool, so you can project from one to another. But when it works with multidimensional raster, currently this geoprocessing tool doesn't work with multidimensional raster. However, all the raster function that we have already enhanced to support multidimensional raster. Say if you have a any like netCDF or of the data of 20 years or how many months, right? Multi-dimensional raster. You can just apply one raster function, which is a reproject raster function. It will reproject the whole cube into the projection that you need. And then you just use a copy raster tool to save it. Then you will get your multi-dimensional projected raster.
Thank you. And as Hong said, that if you want a persistent data set, you can actually do the copy raster. Otherwise, you can actually use the output from function. Correct, Hong?
Right. You can. Yeah. The layer is, as we say, it is dimension aware. So the layer is also reproject the layer is also multidimensional raster. You can just use directly into other type of analysis.
Cool. Thank you, Hong. Next question is for Sharmishta. How can I read large files with many points? For example, stations, time series, trajectories, etc., efficiently in ArcGIS?
Sure.
Sharmishta? Yep.
Yes. If you have station or time series data or like trajectory data, which are all non-gridded data, you can read them using the make netCDF feature layer tool. Or if you are not interested to look at the geometry, you can also read the read your data in the make netCDF table view tool. If you have a large data, it will take some time. It might take some time actually to read the data. We are working on additional capabilities, and we are basically working on improving the performance of this tools.
And hopefully it will also scale and work with large data.
Absolutely, yes.
Okay, thank you, Sharmishta. Hong, the next question is for you. I have some yearly temperature data stored as TIFF files. Can I create a multidimensional raster from this file? Hong?
Okay. Yes, you can. And so TIFF file, it's not like netCDF file or other satellite data. They have metadata in either a metadata file or in the header of the netCDF. But for TIFF, you need to know when the data is captured, right? So normally it's in the name of the data. So what you can do is you create a mosaic, just add the data using raster dataset raster type. So it will add all the data in, and then you can add the field, which is a date field that extract the date from your file name, and then you build multidimensional info out of this, and then that is the multidimensional raster.
Cool.
And you can use this in just like a regular multidimensional raster in analysis.
We have another question from Mahesh. Mahesh is asking, can you comment about the desktop resources needed to support multidimensional raster analysis? Hong, you want to take this question?
Okay, so from what I understand from this question, it looks like is the performance wise, right? If you have large data on many slices, how this analysis is going to work, right? So for multidimensional raster analysis, we support parallel processing. So geoprocessing tools has a very parallel processing has an environment. You can set the parallel processing factor. By default, it will take 50% of your available cores on your desktop, and because we use CRF as the output to store the multidimensional result. CRF support is tile-based. It support parallel write. So actually, is the basic foundation that support multidimensional raster analysis, parallel multidimensional raster analysis.
Right. So Hong, maybe I should ask the follow-up question. So are you saying that we don't really need a special kind of desktop? If your desktop can run Pro, we should be able to actually execute and perform multidimensional raster analysis. If you have more core, more memory, then it will be more beneficial. But there is it's not that for multidimensional raster analysis, you need a special kind of computer.
No, right. So yeah, so regular, like the regular, just the standard desktop just can work with it. And right, if you want to go with large scale, nationwide, high resolution, of course, enterprise with raster analytics can speed up the process, right? But for regular application, the desktop you can use desktop to work with a multidimensional raster analysis.
Thank you, Hong. I guess one last question for you. Does ArcGIS support irregular gridded data?
Irregular gridded data.
Irregular gridded data.
Yeah. So yes. Yeah. Some like netCDF file, they have the dimensional array not regular. But but we can ArcGIS support it. If either if you create from a mosaic data set from it, or you use just the add multidimensional raster tool. What happened is that we actually we check whether it is regular or irregular or not. Then we estimate the average size of the data, and then we interpolate the data on the fly to create a surface. And you can, and by default we use nearest neighbor, but you can choose either interpolate by linear interpolation, or there's also I think a nearest neighbor. So you can choose your own and redefine the pixel size of the surface. Right. So this type of layer created where I'm obviously slower than the regular size because it does actual work on the fly. Right? So then if you want to speed up this kind of service, this kind of data, you can create save a CRF, then it will perform much better.
Cool. Thank you very much, Hong. I think that kind of concludes our Q&A session. We don't have any other session in the queue. So thank you for attending the session and asking all the great questions.
Thank you.
Thank you.
Thank you, Norman.
Thank you,
Thank you for
folks.
joining us.